Raman and FTIR spectroscopy. I want to use this PowerPoint presentation to introduce the National Institutes of Standard and Technology and what actually is done at the NIST administration building in Gaithersburg, Maryland. And they compiled a library of spectral data on molecules of Raman and FTIR spectra. These techniques are a way to help solve crimes for detectives and law enforcement after we identify functional groups. We will need the hydrocarbon spectral database at the NIST. And it is a database of these groups. The NIST Data Gateway provides easy access to many, currently over 80 of the NIST scientific and technical databases. These databases cover a broad range of substances and properties from many different scientific disciplines. Like a photo album, I can use the NIST database to follow your tracks and even know what car and how fast you were driving by the material you left behind. The Raman spectrum for 2-butanone here is shown here, and is a typical FTIR spectrum of a ketone, or the FTIR spectrum. This is another representation of it with overlapping spectral lines. And as you can see, FTIR spectra is reported in percent transmittance versus wave number. And each functional group has characteristic bands and particular wave numbers. What is Fourier transformation? I want to describe this briefly. It is multiplexing. It is grabbing the light all at once instead of nanometer by nanometer as done in a typical spectrometer. Old instruments use a step motor, but they are slow and they vibrate the spectrometer. The Institute of Electrical and Electronics Engineers, or IEEE, National Lab Windows software, provides IEEE 802 protocol boards and software to make our life easier. For cyclohexanol, we are going to check out this website at Augie University as a chemical research spectra of cyclohexanol. And briefly, this is a chart of the regions where particular groups absorb light. As you see, benzene, alkenes, and carbonyls typically absorb infrared radiation between 2,000 and 1,500 wave numbers. Similarly, between 4,000 and 3,000 wave numbers, you have alcohol, amines, triple bonds, carbon triple bonds, and carbon double bonds. Here we have an FTIR spectra of cyclohexanol, which is a picture of this molecule. And it is taken with this camera, the Nicolette 6700 and the research grade Nicolette 8700 FTIR spectrometer series look like this. And inside the spectrometer, you have these typical parts: a light source, a grating, mirrors, and a detector. When a microscope interferometer is introduced into the instrument, it allows us to grab light all at once. It's a typical arrangement of an interferometer where you have two mirrors and a beam splitter to aid in the collection optics. And this is the use of an interferometer. Here you have to the left a coherent light source, and you have mirror 1 at the top, mirror 2 at the far right, and your half-silvered mirror to allow some transmittance to a detector. And this is the Michelson interferometer. And it makes a Fourier transformation of a spectrum. The best way I can explain Fourier transformation is if you had a fire poker a fire poker in a fireplace, and you were possibly heating up the coals. Heat travels through maybe an iron poker, molecule by molecule, till it goes up to your hand. So heat transfer is an excellent way to explain Fourier transformation without a lot of mathematics. The interferometer, again, is composed of two mirrors and a beam splitter. These equations are complicated. All right, first to the first introductory course in chemistry. However, if you could describe or simulate heat traveling through a rod, Fourier transformation helps to enhance our pictures in the same way. And spectra is read again in wave numbers instead of nanometers. And for our molecular library, the Nicolet FTIR spectrometer is the state-of-the-art system. Here's a Raman Nicolet spectrometer. So let's pretend to grab a sample, and let's take a look at some spectra.